Welcome to the F650 Interactive Learning course. Over the course of the Software, Protection, and Control sections, this training CD will demonstrate how to use the F650 relay for a simple protection and control scheme. Given the application shown, where a feeder current is measured by a CT providing current information to the F650 relay, the relay is in charge of tripping the circuit breaker. If the fault is cleared, it will also attempt a reclose of the circuit breaker. The various steps required to achieve the proper relay configuration are presented. These steps are communicating with the device, adapting the relay to the electrical system protected, configuring the overcurrent protection element, preparing the auto reclose function, and configuring the oscillography for recording of trips. The 650 EnerVista setup can be used in two different modes, offline mode or online mode. The offline mode allows viewing, creating, or modifying relay settings without the need of the actual relay. All the work is done and saved on the computer. In online mode, the changes are performed on the relay itself. In addition to live setting change, the online mode permits the operator to visualize the metering and statuses of the relay. The simple protection and control scheme of the Software, Protection, and Control sections will be mainly demonstrated in the online mode. However, the software section will also explain offline mode operation in the Setting Files subsection. Prior to configuring the relay with the aid of a computer, it is necessary to establish the communication between the PC and the F650. In the EnerVista 650 setup software, select the Communication menu and click on Computer. This will open a new window that shows the communication parameters necessary in order to establish communication. For this example, a serial communication to the front USB port is configured. Configure the slave address and the baud rate to match the relay settings. In the default configuration, the slave address is 254 and the baud rate is 19,200. Recall that the relay configuration for the slave address and baud rate is displayed in the main screen of the 650 display on the last line. The communication port has to match the port assigned by the computer to the USB driver. To determine this port, right-click on My Computer and select Manage Item. In the new window, select Device Manager and search for ports, COM and LPT. Open the ports to see what COM port has been assigned to the USB driver. Alternatively, in order to communicate by the Ethernet port, the control type should be selected as Modbus TCP. The communication control is shown at the bottom of this window. With the relay not communicating, a message states that the 650 setup is not talking to a 650 and the ON button is enabled. Pressing this button will initiate the communication with the 650. Once the communication is established, a message states that the 650 setup is talking to a 650 and the OFF button is enabled. Pressing this button will terminate the communication with the 650. Once the communication is established, press the OK button to close the communication window. The status bar at the bottom of the main window will indicate that the mode is online, the model, and the firmware version of the relay attached to the computer. For further information regarding the other parameters, refer to the instruction manual. Before diving into the relay settings, it's worth taking a step back and understanding the philosophy of how these settings are organized. As previously mentioned, the 650 relay comes loaded with a default configuration. This section will present the two main aspects of settings: general organization of settings and the distinction between parameters and flex operands. General organization. The figure shows the arrangement of the 650 relay settings. We have the product setup, system setup, protection elements, control elements, and inputs and outputs. The product setup refers to all the settings that control how the users interact with the machine. These settings are not necessary for the protection and control functionality of the relay. They define aspects such as the communication parameters, the fault report and oscillography, and the time settings. As you can see, these pieces of information do not help the relay to better protect the electrical system. Rather, they help the user interact with the machine and obtain useful information. In system setup, we define the electrical system that the relay has to protect. Parameters such as breaker status, CT and VT ratios, system nominal frequency, phase rotation, and maximum number of breaker openings per hour can be found under here. Protection elements contains all the protection functions of the three setting groups. Whether a phase time over current element or a voltage element has to be configured, it can be found under protection elements. The control elements are the relay functions that are not protection functions but are auxiliary to protection relays and often found together with the protection elements inside the same device. Auxiliary functions such as auto reclose and synchro check, or supervision functions such as breaker failure or VT fuse failure, can be parameterized in the control elements category. Finally, the inputs-outputs category regroups, as its name implies, all the settings related not only to the physical contact inputs and outputs board, but also the communication I/Os, or as they're called in the 650 family of relays, the remote inputs and outputs. Parameters versus flex operands. There are two different aspects of 650 configurations that need to be well understood prior to proceeding with the task of configuring the relay. They are parameters and flex operands. Some aspects of the configuration rely on parameters. A parameter can be either a number or an element of a list. For instance, when enabling a time over current function, a choice is made between enabled or disabled from the list of elements. When configuring the pickup value for this function, a number is used, for example, 50 amperes. Whether pertaining to a number or an element from a list, we will refer to this aspect of the configuration as a parameter. The other aspect of the configuration is called flex operands. Flex operands is the term used in the 650 and UR families of relays to refer to the binary statuses existing inside the relay. These binary statuses can be used as operands, as in an input to a building block, in order to provide extreme flexibility when the time comes to configure the relay. Some examples of flex operands are the status of a binary input, the pickup of a protection element, and the closing permission of a synchro check element. One simple illustration of the use of flex operands is an instance where it is desired to block a certain protection element during breaker maintenance. In this case, the flex operand associated with a contact input can be used to block the protection element. It is important to understand the difference between these two aspects because the parameters and the flex operands are not configured at the same place within the software. To provide a clearer understanding of the difference between parameters and flex operands, let's examine a specific example, configuration of the oscillography. Clicking on the Set Point menu and selecting Product Setup followed by Oscillography makes its associated Parameters window appear. From this window, it is possible to enable the oscillography, configure the trigger position and the samples per cycle, etc. Notice that there is no provision made either for the triggering signal or the binary signals to be recorded together with the voltages and currents. In fact, both the triggering signal and the binary signals are flex operands of the relay. Flex operands can be found under the Relay Configuration and Logic Configuration headings in the Set Points menu. In Relay Configuration, we make use of the flex operands. In Logic Configuration, we combine the various flex operands into logical equations to generate new flex operands, which can in turn be used inside the relay. In our oscillography example, it is possible to configure the trigger signal and the binary signals under Relay Configuration. The 650 relay has provision for 16 different digital channels and one oscillography trigger. Note that each of these 17 signals can be a logical equation. The work of the protection and control engineer when configuring the 650 relays can be split in two tasks. The first task is to program the parameters of the various elements to ensure that each building block works the way it is meant to. The second task is to connect these blocks together by the means of the flex operands, such as to ensure the proper functioning of the complete 650 relay. These two tasks are represented for a simplified 650 configuration where the building blocks or elements and their parameters, the first task, are represented as rectangles, and the second task, the interconnection of the blocks, is shown as solid lines connecting the elements. To summarize this section, we have seen how the relay settings are organized in categories: product setup, system setup, protection elements, control elements, and inputs and outputs. Also, we have seen how the parameters of each element can be found under the above categories, and how the flex operands, or binary statuses related settings, can be found under relay configuration. it is a good idea to ensure that you have a solid understanding of this section before proceeding with the rest of the training. As introduced in the previous section, the product setup category of settings is concerned with the configuration of the human-machine interface. It contains the settings that facilitate the gathering of information that are useful to the end user. Whether it is the oscillography to record pre-fault and fault current and voltage, or the Modbus user map that allows grouping of useful information for a SCADA system, product setup eases the configuration of how the user interfaces with the relay. Selecting product setup followed by communication settings, it is possible to modify the serial ports and Ethernet connection parameters. Let's first look at the serial port settings. From this window, it is possible to modify the COM1 and COM2 baud rate. Remember that COM1 is the rear side communication port, while COM2 is a multiplexed front and rear communication port. Note that if you communicate with the relay through the front panel and you modify COM2 settings, you might lose communication. Similarly, if you change Ethernet settings while you're communicating with the relay via Ethernet, you might also lose communication. If we consider the network or Ethernet window, then we can configure the relay IP addresses. It should be noted that even though the relay has only one Ethernet physical port, COM3, it has two IP addresses located in the two settings tabs. To change the relay IP address, simply click on each of the settings tabs and enter the value. Once all the settings are changed in a given tab, press the Store or OK button. The EnerVista 650 setup software uses the Modbus protocol to communicate with the relay. In order to set an appropriate address for each COM port, navigate to the Product Setup menu, enter the communication settings, and select the Modbus protocol item. After entering the Modbus address for COM1 and COM2, as well as the Modbus port number if using Modbus TCP, press the OK or Store button. The last settings that we will modify in the product setup are those of the oscillography. After the relay is completely configured to protect the electrical system, it is important to be able to record an oscillography when a fault occurs. An oscillography is a data capture of the currents, voltages, and various other binary information in the relay. It can help detect why a relay tripped and detect the reason behind faults. To configure an oscillography record, navigate to Product Setup again and enter the oscillography menu. A function enabled means that the oscillographic function is ready to record oscillography according to its configuration. A trigger position at 30% means that 30% of the complete oscillographic record time will be done prior to the trigger signal going from 0 to 1, while the remaining 70% will be recorded after the trigger signal is raised, allowing for a certain amount of pre-fault signal, followed by fault and possibly post-fault voltage and currents. All current and voltage samples used for protection are recorded at 64 samples per cycle. While providing a finer and more truthful representation of current and voltage, it also reduces the length of the oscillography. The two following settings deal with oscillographic record management. The maximum number of oscillography will determine the number of oscillographies recorded, and conversely, the greater the number of oscillography records means that each record will be shorter. The automatic overwrite setting allows chained oscillographies during the fault. The maximum allowed value to be stored as a chained oscillography is 1 megabyte. In this case, even if the trip continues during a time longer than the associated 1 megabyte of memory, the relay will stop storing the oscillography in RAM memory until the complete record has been saved in non-volatile memory. The oscillography module will be reset once the data has been completely stored in flash memory, and the trigger oscillo state is deactivated. This section will illustrate how to program the relay to properly detect current and voltage levels. In order to properly meter and provide protection, the relay must know the specifics of the system it is connected to and how it is connected to the system. To access the settings that provide the relay with system information, select System Setup from the Set Points menu. Under the General Setting item, you will find all of the settings for the current and voltage transformers installed in the system. Note that the CT should be selected so that the nominal current in the system falls within 50 to 100% of the primary rating of the CT. Depending on the grounding connections chosen, the ground CT ratio will be entered here for either the standard or sensitive ground CTs. If a residual ground connection is used, program the CT primary to the same value as the phase CTs. Attention must be paid to the fact that ratios have to be entered here independently of the CT secondary value. For example, in the case of a 600-5 CT, then a ratio of 30 must be entered as the phase CT ratio rating. The voltage transformer, or VT configuration, must also be set here in order to allow the power metering and to enable the synchro check function of the relay. As discussed earlier, there are two separate VT connections. They are the three-phase line connection and the single-phase bus VT. We will first program the line VT. Select whether the VTs are configured as a Y or open delta connection. The line nominal VT secondary voltage will be the nominal phase-to-phase system voltage divided by the VT ratio. If the connection is selected as Y, you will need to divide the nominal secondary voltage by √3 and program this value. The VTs must be selected so that the secondary voltage falls between 50 and 250 volts. The fourth VT input is called the auxiliary voltage, or VX. Depending on the specific application, this VT input can serve either as a neutral voltage input or, for instance, a bus voltage. In the first case, you would configure the auxiliary voltage to VN, while in the second case, you would configure it as VX. The nominal frequency should be configured to match your electrical system frequency. Lack of configuring it properly will give metering error that might cause the relay to operate in unexpected ways. Finally, for the relay to be operational, ensure that the relay out of service setting is configured as disabled. Otherwise, the I/O boards and most protection and control functions are effectively disabled. The next set of parameters to consider in the Set Points menu are the protection elements followed by the control elements. We will provide a detailed look at the protection and the control elements in the protection and control section of this CD. But for now, let's take a glance at what is available in the relay via the software. The 650 relay is truly a multifunctional relay, and this can be easily seen when navigating through the protection element and control element menus. Protection elements. There are a total of 28 protection elements, including phase and ground over current, over and under voltage, power functions, and directional supervision for the current and power functions. Taking the phase TOC, or time over current, as an example, we can navigate to the protection elements, open the phase current, and select the phase TOC high option. The new window permits us to modify the phase TOC element parameters. There are three tabs at the top of the window. Phase time over current high 1, 2, and 3. These tabs refer to the three setting groups that are available in the 650 relay. The relay can operate in single setting group mode or three setting group mode. This configuration is selected at Set Point, Control Elements, Setting Groups. If the setting grouping permission is enabled, only one setting group can be active at a time, 1, 2, or 3. This setting is disabled by default, which means that all three groups will be active at the same time. In any case, the individual element itself must be enabled for it to operate. In the case of the time over current, the input can be either a phasor or RMS value. If choosing a phasor, then only the fundamental frequency is taken into account when comparing the measured current with the pickup level. This is accomplished with Fourier transform filtering. If choosing an RMS value, then the full frequency spectrum is considered. The following setting is the pickup level. It can be set anywhere between 50 milliamps to 160 amps. Note that the pickup value is set in secondary amps independently from the CT secondary nominal amps. The following two settings, the curve and the TD multiplier, allow a precise selection of the time versus current curve that will be used for the phase time over current element. The reset setting can be chosen to be instantaneous or linear. This refers to the time it takes to reset the counter once the current drops below the pickup value. In modern relays, it is common to select instantaneous. The linear reset option simulates the induction disk that used to exist in electromechanical relays and is used to maintain selectivity when retrofitting old installations. Finally, the voltage restraint characteristic modulates the pickup value of the overcurrent element in function of the measured voltage. It is normally used for relays installed near generators where a short circuit would cause the voltage to drop and the short circuit current to be lower. Control elements. The control elements are functions, but are not used in the protection scheme in the strictest sense. However, they are usually found in protection relays since they can make use of the metering and I/O performed by the relay. We will find elements such as the control of the setting group, frequency elements, synchro check, auto reclose, and several others. The protection and control section of this training CD will go into more details of these elements. The Relay Configuration menu is where the user can configure the inputs, outputs, LED configuration protection element signals, and graphic display configuration, among other settings. It contains an extensive list of definable settings in a single menu. The various relay configuration settings are set using flex operands that are obtained from the internal states of the F650 or resulting from the compiled equations on the PLC logic editor. Let's take a closer look at the relay configuration. To access the relay configuration, go to Setpoint, Relay Configuration. In the Relay Configuration menu, you can see various tabs. The first tab, the Outputs tab, is used to program and define what operates each contact output in the F650. Click on the Outputs tab to access it. The built-in configuration already has some contact inputs defined. In order to configure the output, select it by clicking on the checkbox on its left. The user can also define a custom name to make the identification of the outputs easier. Finally, the user can choose what internal status or flex operand will make this output operate. This can be chosen via the source drop-down list. This drop-down list contains all of the flex operands that can be used. To save these changes, click on Store. This will send the changes to the relay if it is connected in online mode, and will save them to a settings file when working in offline or file mode. In order to operate this contact output using more than one signal, check the OR checkbox. The user can then select various signals for the source. If a flex operand programmed in this OR gate operates, the contact output will consequently operate. Next, let's consider the LED tab. The F650 has a total of 15 user-configurable LEDs that can be programmed to convey the status of the power system. They can be used to show an alarm, trip, or any other binary status. The first 5 LEDs are latched. Latched LEDs turn on once the operating signal or flex operand that operates them is activated, creating a logic state 1. These LEDs remain on even after the flex operand deactivates or returns to a logic state 0. These LEDs must be reset manually. One way to do this is to press and hold the Escape or ESC key for 3 seconds on the front of the relay. The remaining LEDs are self-resetting, which means that the LEDs will reset automatically once the flex operand that operates them turns off or deactivates. Similar to the outputs, the user can assign a name to each LED and an operating signal. Assigning more than one flex operand to operate that LED is accomplished by checking the OR box and then assigning more than one source. Another useful menu in the relay configuration is the Protection Elements tab. Here, the user can assign flex operands that can initiate or block certain protection functions, reset LEDs, or change setting groups. For example, sometimes it is convenient to have 2 different setting groups. The first setting group can be used for normal operation, while the second group can have more sensitive settings and can be used during maintenance. Ideally, during maintenance, operators would turn on a switch on the protection cabin that switches to maintenance group. The switch status can be conveyed to the F650 via contact inputs. Let's program the first and second group to be activated via contact inputs 1 and 2 of board F, respectively. In order to change the active group of settings from the first group to the second group, first, go to the Protection Elements tab in Relay Configuration and find Group 1 Act On and Group 2 Act On in the list Protection Elements. Enable them by clicking on the checkbox, and then assign the correct contact input to each protection element. Finally, Note that the EnerVista 650 software keeps track of the amount of memory used by the relay configuration and PLC logic equations, as well as the total used memory. This information is displayed on the right side of the relay configuration window. Switchgear is any primary equipment in the power system that is used to isolate electrical equipment, including circuit breakers, isolators, or fuses. In the F650 relay, it is possible to configure up to 16 switchgear elements. These include one main circuit breaker, while the remaining 15 can be used for other switchgear, such as additional circuit breakers or isolator switches. The configuration of switchgear is carried out in the Relay Configuration menu under the Switchgear tab. To enable a switchgear, click on the checkbox on its left. Next, in the Contacts column, select what breaker or isolator status is used in order to define whether the breaker is open or closed. The selection can be 52A, contact type A, showing the same status as the represented element; 52B, showing the opposite status to the represented element; 52A plus B, where both types of contacts are used, or none for no status monitoring. In this example, we will choose 52A plus 52B, which means that the switchgear will be closed whenever the 52A status is active or at logic 1, and when the 52B is inactive or at logic 0. Conversely, the switchgear will be opened when 52A is inactive and 52B is active. The status monitoring will be in error in any other combination. These statuses are usually hardwired to the relay's contact inputs. However, they can also be conveyed via a communication network. They are defined in the Contact A and Contact B columns. Since we have previously chosen 52A and 52B, we have to configure both of the statuses. In the Contact A and B columns, there is a list of all possible flex operands with signals that will convey the two switchgear statuses for 52A and 52B, respectively. For this example, we shall choose two different contact inputs to Contact A and Contact B. We will use the contact inputs 1 and 2 of board F, respectively. You can also associate an open text, closed text, and error texts for 00 and 11 errors. These error texts appear whenever the status of the 52A and 52B are the same, either 00 and 11. Any of these 16 switchgear elements can be defined as the main circuit breaker of the F650. To accomplish this, go to System Setup, Breaker, Breaker Settings. In this menu, many different breaker settings are possible. In order to define which of the configured switchgear corresponds to the main circuit breaker, select the switchgear's number, 1 to 16. Here, the user can also set the maximum openings of the breaker and the maximum opening per hour. If a maximum of openings is not desired, select the highest number of the settings range, 9,999. As mentioned before, the F650 is a complete bay controller and protection relay. As such, the F650 relay can be programmed to perform up to 24 different operations, which can be executed from the HMI front plate or from the software. The relay allows the possibility of choosing whether to execute all the operations locally, remotely, or by a push button in the front plate. The operations can even be configured to be operated via the graphical mimic display if your relay has the graphic front plate option. These operations could be a breaker or isolator opening command, a closing command, or even a reset of the relay's stored data. Operations are also configured in the Relay Configuration menu under the Operations tab. To enable an operation, select its checkbox under the Select column. The user can also define a custom name for each operation in the Command Text column. The next two columns configure the interlock type and interlocks. An interlock is a condition that must be fulfilled for an operation to be performed. The interlock type can be set to logic, in which case one or more conditions must be fulfilled for the operation to be executed, or it can be set to none, which means that no interlock is used. In the interlocks column, the user can choose which condition should be fulfilled in order to allow the operation. For example, if your operation is a close breaker command, it is important that the circuit breaker is only closed when synchronization conditions are present. To accomplish this, choose the interlock type as logic, and then in the interlocks column, click on Press for Logic. Here you can see a predefined logic of 3 AND gates whose outputs are input to a 3-input OR gate. The output of this OR gate is the interlock condition. In order to add an interlock condition, click on the checkbox under the Select column, and then under Source you can select any flex operand inside of the relay. For this example, we shall choose SynchroCheckOp. This way, the closing operation will only be allowed if we have synchronization conditions. In order to correctly set up the SynchroCheck function, please refer to the Protection and Control section of this training CD. The final state type setting defines whether the operation requires, in addition to the interlock logic, any other conditions to determine a success condition. If so, select Logic. Otherwise, select None. The final state setting defines the success condition of a programmed operation if the previous setting, final state type, was set as logic. The next 3 options allow the possibility of executing the operation via a front key, a contact input, or a virtual output that was previously defined at the Logic Configuration tool with PLC logic. Finally, the timeout setting defines the period during which the operation command will remain activated, waiting for a success condition. If the success signal is received before this period expires, the command signal will be removed and the timer reset. If the success condition is not received within this period of time, the operation is considered to be finished once it has timed out. The configuration process of a 650 relay involves the use of 2 files. While the files of type or extension 650 contain the complete configuration of the relay, the PEP files are merely a tool to configure the programmable logic that is later integrated to the 650 file. We will pay more attention to the PEP file and graphical logic configuration of the 650 relay further into the training. For now, we will concentrate on the 650 file. Since we have previously established communication with the relay, the file menu of the software will enable 2 new menu items: Get Info from Relay and Send Info to Relay. The Get Info from Relay choice will read the relay settings and save them on the computer at the location and with a file name selected by the user. Conversely, the Send Info to Relay choice gives the opportunity to the user to select an existing relay setting file and send it to the relay. When doing this, the new settings will become effective and the relay will behave as previously defined. In order to send a setting file to the relay, the order code and the firmware version must match. If it is not the case, sending the file is aborted. Note that the file menu shows a config file converter that allows converting an existing setting file to a new model or firmware revision. In this section, we will examine how to control the circuit breaker. First, we shall select some inputs and configure them to monitor the status of the breaker, as we have already done in the breaker and switchgear section. And then we shall do the same with some outputs to operate the breaker. To perform these actions, we will first configure the human-machine interface. Navigate to Setpoint, Relay Configuration, HMI. Place a switchgear symbol on the one-line diagram and associate the figure to its corresponding switchgear number by clicking on it and selecting a switchgear that has already been configured. For details on how to configure switchgear, please refer to a previous section of this CD. In order to monitor the status of the breaker, switchgear, and the board that is being used, open the monitoring panels in the following addresses: Actual, Status, Breaker. Actual, Status, Switchgear Status, Switchgear 1. Actual, Input Outputs, Contact Inputs, Board F. Now we shall select and configure the contact outputs to operate the relay. In this example, we shall use the F35-F36 output contact to trip the breaker and the F32-F33 to close it. Remember that there are specific contact outputs for these operations depending on the relay model. This is clearly specified in the wiring diagram of the F650 manual. Navigate to Setpoint, Relay Configuration, Operations, and configure the Open Breaker and Close Breaker operations. To do so, tick the Operation 1 checkbox. Write the command text Close Breaker and select which key to use to operate it from the tab in the Frontal Key column. Select the I key to close the breaker. For the opposite operation, select the Operation To checkbox. Write the command text in the nearby column and select a key to open the breaker, in this case, the O key. The last step is to configure the contact outputs of the relay. We will start by navigating to Set Point, Relay Configuration, Outputs. Here, select the Contact Output Operate 07 and 08 checkboxes, the ones related to the contact outputs we selected to operate the breaker. In the Source column, select as sources the operation bits 1 and 2 respectively, and click OK. However, remember that when the relay is in proper operation, the user will have to configure a logic so that the relay operates the breaker when some protection function orders it, or when an operator orders it manually. To accomplish this, check the OR or NOT columns and select the sources by clicking on the Sources column. Finally, we are ready to operate the breaker. The way to do it is either by pressing the buttons on the front plate of the relay as we have configured, or using 650 Setup, navigating to Operations, Open Breaker, Close Breaker. Remember, the user can monitor the breaker, switchgear, and the contact inputs in Board F, discussed earlier in this section. This section will demonstrate how the logic inputs and outputs are set up in the default 650 configuration. They allow proper detection of the breaker status, blocking of the protection function, and management of the auto-reclose function. In order to detect the condition of the breaker, the relay needs to be connected to the 52B auxiliary contacts of the breaker. The relay uses logic inputs to detect the changes in the breaker auxiliary contacts. If 52A or both 52A and 52B contacts are required, the relay configuration can easily be modified. This is covered in the Relay Configuration section. Contact inputs. The default configuration of the 650 uses the first logic input, CC1, to detect the breaker position by connecting the 52B auxiliary contact of the circuit breaker. The following 5 inputs block various protection functions when asserted, while the 7th and 8th inputs are respectively used to initiate the auto-recloser from an external source such as another protection relay, and to block the auto-recloser, for instance, when performing circuit breaker maintenance. Other functions can be assigned to the logic inputs using the logic editor. There are 2 additional parameters that are necessary to examine: the voltage threshold and the debounce time. Navigating to the Set Point menu, select the Input-Output choice and open Board F of the Contact I/O. A new window will open. Here, it is possible to modify the voltage threshold value, which is the voltage necessary to assert the logic inputs. It is generally set to a value of approximately 80% of the substation battery nominal voltage. Note that a different setting can be given to the A and B blocks of Board F. The A block is the first half of the inputs. In our example, logic input CC1 to CC8. Block B is the second half of the inputs, CC9 to CC16. Contact outputs. In the default relay configuration, the output contacts are organized to operate as shown. The 2 main output contacts are 07 and 08 on Board F, which are the close and open contacts respectively. The close contacts are associated to the auto-reclose function and the manual close command. The trip contact, 08, is associated with all protection functions that should be opening the circuit breaker. It is also activated by the manual opening command. The remaining output contacts are configured by default to provide information about the auto-reclose function and the pickup status of some of the important protection elements. All of the contact outputs have the same current rating and characteristics. Each of them, including the trip and close contacts, can be reconfigured if necessary. The procedure is covered in the Relay Configuration section. The F650 relay provides the ability to store files in the hard drive of the relay. This feature is located under Communication and Upload Info Files to Relay or Download Info Files from Relay. With this tool, the user is able to store in the relay .650 files, which contain protection and control settings, relay configuration and compiled logic equations, and PEP, AUT, and LIB files, which contain the logic configuration projects necessary to modify the logic. Take into account that without these last three files, it is possible to modify the settings in the relay, but not the logic. Also note that this is just a storage option, and that no settings will be operative if the files are merely uploaded. To take advantage of this tool, navigate to Communication, Upload Info File to Relay. A window will prompt the user to select which files to upload. Remember to check the relay IP address. Once the files have been selected, press the Upload File button. A window will inform that the files have been uploaded correctly. To download files, the process is almost identical. Navigate to Communication, Download Info File from Relay. Confirm the relay IP address. Then, save the files on your hard drive. A message will inform that the files were saved correctly. In this section, we will examine how to configure the inputs and outputs of the relay. Start by navigating to Setpoint, Inputs/Outputs, Contact I/O, and select the desired board for configuration. In this example, we will select board F. A window will appear with all the configurable parameters. This window has three columns. The first column displays the parameters. The second allows the user to input a value for the parameter, and the third shows the range of possible values of each parameter. Let's take a closer look at some of these parameters. The voltage threshold is the value beneath which the relay shall not interpret a signal as a logical one. This value can be set between 10 and 230 volts. For example, if the control voltage is 24 volts DC, then an adequate voltage could be 17 volts. Note that the threshold must be less than the control voltage that will activate the inputs, but higher than any electrical noise expected in the substation. The debounce time is the time the relay will wait before interpreting a signal. If a logic 1 is received but maintained for less than the debounce time, then it is considered to be noise and not an intended signal. The next 16 parameters correspond to each of the inputs on the board. The input type defines how the input will work, whether it will be activated by a positive or a negative signal, or by a positive or a negative edge. The next 16 parameters are the delay input times. These settings are only used for slow switchgear applications. The output logic elements correspond to the 8 outputs on the board and can be either positive or negative. Next, the user can specify the output types to be used. Types include normal, pulse, or latched. If a pulse output type is selected, the time length of each pulse must be set using pulse output time. Finally, press OK to enable the configured settings. Depending on the board type, the amount of inputs and outputs will vary, but the parameters will remain the same for each board. Virtual inputs are internal logic signals that can be written directly using EnerVista's 650 setup software. These virtual inputs can be latched or self-reset. Latched virtual inputs remain at the set value until they are changed by communications. Self-reset virtual inputs remain active during one PLC cycle. There are 32 virtual inputs available of each type. To write a virtual input, select Setpoint, Inputs/Outputs, Virtual Inputs. The new window will display all the virtual inputs. Tick the checkbox next to each input and press the Store button. To clear a latched virtual input, click again on the checkbox and press Store again. To monitor the status of the virtual inputs, go to Actual, Inputs/Outputs, Virtual Inputs, Virtual Input Latched, Virtual Input Self-Reset. The texts assigned to virtual inputs in the relay configuration screen are only for file management. They are not sent to the relay. Remote inputs and outputs provide a means of exchanging digital state information between Ethernet network devices. The F650 relay is able to provide GOOS or GSSE messages. GOOS messages, which stands for Generic Object-Oriented Substation Event, and GSSE messages, which stands for Generic Substation State Event, are two different communication standards. GOOS is increasingly being used in the automation of modern substations. To enable remote inputs and outputs, navigate to Setpoint, Input-Output, Remote Comms. It should be noted that only F650 relay models with the IEC 61850 software option have the remote comms feature enabled. From this window, remote comms can be enabled by selecting their type, Goose or GSSE. Selecting the Goose option, the user can now use remote inputs throughout the relay to perform various actions, such as generate or send an alarm, operate logic, or activate contact outputs. For example, the relay can be configured to use a received remote input to reset the LEDs on the relay. This can be accomplished by navigating to Setpoint, Relay Configuration, Protection Elements tab, and defining Remote Input 1 as the source for LED reset input. As discussed in the hardware section of this CD, trip circuit supervision circuits are auxiliary circuits that monitor the tripping circuit to ensure its proper operation. This is accomplished via two main trip circuit supervision features. The first is to use current supervision in the tripping circuit, which is designed to protect the relay tripping contact output by sealing it closed in the event that the breaker fails to open. This prevents the trip contact output from breaking open operation currents, which it is not intended to handle. The second feature is to use voltage supervision to check the continuity in the tripping circuit, certifying that it is ready to operate when needed. Please note that there is no need to activate these features when using supervision circuits. This functionality is internally prepared for their use. The user can then use the internal states to operate an alarm, LED, contact output, or even use these states in the PLC logic editor. For example, if we wanted to set the sixth LED on the front of the relay to activate if continuity in the tripping circuit was disrupted, we would navigate to Setpoint Relay Configuration. Under the LED tab, we can select the sixth LED and name it Trip Supervision. Through the Actual Values menu in the EnerVista 650 setup software, the user can monitor all the activity in the network the relay is protecting. This feature can be used to monitor real-time data such as the status of any operands, inputs and outputs, LEDs, currents, or voltages. It also provides the ability to access the data records in the relay, including the snapshot events, fault reports, waveform captures, etc. To monitor the operation of the relay front LEDs, navigate to Actual, Front Panel, LEDs in the 650 setup software. The figure that appears is a representation of the LEDs on the front plate of the relay. All of them will be lit in the same color as on the actual relay. For more details on the F650's front LEDs and their default configuration, please refer to the hardware section of this CD. Under the Actual Status menu, the user is able to access panels that monitor the status of all the signals in the relay. In a status window, when the light next to the name of the signal is lit, the signal is active. Conversely, if it is not lit, the signal is inactive. In this section, we'll examine some of the basic status signals which can be monitored by the F650 relay. These include signals for operation bits and breakers, as well as an example of one of the protection and control elements. First, navigate to Actual, Status, Operation Bits Status panel. These 24 bits are the outputs of each possible operation module programmed in the Setpoint Relay Configuration Operations window. Under the Breaker Status panel, the user can monitor the status of the main breaker. The breaker status can be open, closed, or undefined. The undefined option will light up when the breaker is monitored by a 52A and a 52B auxiliary contact, and both are in the same state, either open or closed. To better understand monitoring of the statuses of all the signals involving a protection function, let's look at the phase current elements as an example. In this panel, all of the possible signals involved in current protection elements are monitored. The user can see signals for all three setting groups of the IOC and TOC protection elements, including the high and low options. There are pickup and operation signals per phase, as well as general signals based on all three phases. There are also operation and blocked signals for the phase directional overcurrent elements. Similarly, the user can monitor the status of the other types of protection functions, such as the voltage, power, ground, and neutral current protection functions. To highlight the monitoring of control element signals, we shall use the SynchroCheck function as an example. In the SynchroCheck monitoring panel, the monitored signals that appear are the SynchroCheck blocking input, which blocks the synchronism unit, the SynchroCheck operate, an operation permission in live line or live bus conditions, the SynchroCheck close permission, an operation permission under any circumstances, and the SynchroCheck condition operate, an operation permission following the programmed logic. The next three signals deal with voltage difference. They indicate if there is a dead line dead bus, dead line live bus, or a live line dead bus condition. The slip condition indicates whether the frequency slip condition between the line and bus voltages is fulfilled. The next two signals indicate which of the frequencies is higher. And the final two signals highlight the frequency difference between the line and the bus. For more details on the monitoring of protection and control element signals, please refer to the F650 manual. Apart from the statuses seen in the basic status section, there are many other signals that can be monitored. Let's take a look at some of the most useful signals for the typical user to monitor. In the F650, there is an option to view many of the system statuses, whether they are enabled or not. This includes all of the protection functions in the relay, plus some other functions whose objective is to report and monitor faults in the system. This panel is located under Actual, Status, Protection Summary. In this panel, the user can view which of the different protection functions are enabled, indicated by a lit LED next to the protection function, and which are not. Similarly, navigating to Actual, Status, Snapshot Event Summary shows a list of all the snapshot events the relay can generate for all the protection, control, and input and output elements, showing their statuses. In this panel, the user can find signals such as events in input-output boards, events involving overcurrent functions, voltage functions, current directional elements, control events such as breaker failure, VT fuse failure, SynchroCheck, and auto-reclose, as well as events related to the switchgear, breaker settings, remote inputs and outputs, and analog comparators. Under Actual, Status, Switchgear Status, the user can view the statuses of all the signals related to the switchgears programmed in the relay. Recall that switchgears are configured via Setpoint, Relay Configuration, Switchgear. Each switchgear has a series of inputs and outputs which include the following. The switchgear XA input will light up when the input associated to that switchgear contact A is activated. The switch XB input will light up when the input associated to that switchgear contact B is activated. The switch XA status is the status associated to switchgear contact A. It is activated once the time required for the switchgear module to acknowledge contact A has expired. The switch XB status is the status associated to switchgear contact B. It is activated once the time required for the switchgear module to acknowledge contact B has expired. The switch X open lights up when the associated switchgear is open. The switch X closed lights up when the associated switchgear is closed. The switch X00 error is the output that represents the switchgear status 00 considered as abnormal. The switch X11 error is the output that represents the switchgear status 11 considered as abnormal. The switch X open initiation is a programmable input that indicates the initiation of the opening operation for the considered switchgear. The switch X close initiation is a programmable input that indicates the initiation of the closing operation for the considered switchgear. The switchgear X failed to open is an output that represents a failure to open from the associated external device when the opening time is exceeded. The switchgear X failed to close is an output that represents a failure to close from the associated external device when the closing time is exceeded. The F650 also has the ability to monitor elements and signals related to the records in the relay. This information is located under Actual, Status, Record Status, Fault Reports. Let's examine the monitored signals found here. The fault report trigger indicates whether the signal that initiates the calculation of the distance to the fault has been activated. The clear fault reports indicates a reset of the fault reports. The fault date shows the date and time of the last fault produced in the relay. The fault type states the kind of the last fault produced in the relay. For example, phase to ground, phase to phase, three-phase, etc. The fault location indicates the location of the last fault produced and registered by the relay. Fault report number displays the number of fault reports available in the relay. 10 is the maximum. The last signals we shall look at are the ones related to timekeeping. These are the SNTP failure and the IRIG-B failure, which are found under Actual, Status, SNTP IRIG-B. Here, the user can determine if there is a failure in any of these signals. For further information on the status monitoring of other signals, see the manual. In this chapter, we shall see all the metering possibilities the F650 relay offers. All the data shown in the metering tables follows the same format. The left column displays the parameter names, the middle column shows the values of the parameter, and the right column shows the units of this value. We shall start with primary value. Let's start by examining primary values. First, open the currents table, which displays all the parameters, measurements, and calculations related to currents. We shall start by examining the elements in this table. The first three parameters show the CT ratios for the phase currents, the ground current, and the sensitive ground current. The next six elements are the current angles of the phase, neutral, ground, and sensitive ground currents. The phasor primary current magnitudes display the current value in RMS of the fundamental frequency of the phase, ground, sensitive ground, and neutral currents. The fundamental frequency is the frequency that is set in the general settings menu, usually 50 or 60 Hz. The user can also monitor the RMS values of the phase, ground, and sensitive ground currents. Here, RMS means that the currents shown are unfiltered, so they will display the value of the current that includes all frequencies present in the signal. And finally, the RMS values of the sequence components and the proportion of load capacity used are also displayed. For voltages, the parameters shown are very similar. The first one is the PT ratio, followed by the angles of the phase-to-ground voltages, including the three phases, neutral, and auxiliary values. Next, the angles of the phase-to-phase voltages are displayed. The magnitudes of the sequence voltages, phase-to-phase and phase-to-ground voltages, including the neutral and the auxiliary values, are also shown. The last two parameters in the voltage table are the bus bar and the line voltages. The values monitored in the power table are the real, reactive, and apparent power and power factors of each phase and the addition of the whole system. In the energy table, the measured magnitudes are the active and reactive energies in both the positive and negative direction. Finally, the last of the primary values that is monitored is the demand. The metered magnitudes are currents and power. Among the current values, this table displays the phase, ground, sensitive ground, and negative sequence currents. For power, this table shows the active, reactive, and apparent values. All measurements in the demand table include the actual value, the highest demand since the last reset, and the date of the maximum demand. Next, we shall take a look at the secondary values the relay monitors. Again, we shall start with the currents. The phase, neutral, ground, and sensitive ground currents, the phasor values, that is, the RMS values of the main harmonic, and the RMS values of the measured currents are shown here. The user can also see the RMS values of the sequence components, positive, negative, and 0. The secondary voltages that are metered are the phasor value of the phase-to-phase, phase-to-ground, and neutral voltages, the RMS values of the sequence components, the phasor value of the auxiliary VT, the nominal voltage, the line voltage, and the bus voltage. The last of the secondary values measured is power. Similar to the primary power table, this table displays the real, reactive, and apparent power and power factors of each phase and the addition of the whole system. The next option in the metering menu is to view a phasor diagram. In this diagram, select the phasors to be viewed by ticking the checkboxes in the left. The final option is to view the frequencies table. In this table, the user can see the line and bus frequencies and the derivative of the measured frequency. The menu Actual, Inputs, Outputs shows the status of all the signals the relay may send or receive, all the contact, virtual, and remote outputs and inputs. Navigate through the menu to find whichever signal panel you wish to display, select it, and a window will appear showing a list of signals. Beside the name of each of these signals, there is an imitation of an LED which will be lit when the signal is active. As a reminder, recall that contact inputs or outputs are physical signals on the relay, meaning they represent a literal contact that opens and closes. A virtual input or output is an internal state of the relay, often the solution of an equation. And finally, remote inputs or outputs are a way of exchanging digital state information between Ethernet network devices and therefore are similar to virtual signals. In the Actual Records window, the user is able to find all the information involving the power system being protected. In this section, we'll look at some of the fundamental recording tools available in the F650 via its software, including snapshot events and oscillography. In the next section, we'll explore some of the more advanced recording features. Snapshot events. Found under the Event Recorder menu, the snapshot events make a record of every event that happens involving the relay. Each event is numbered and marked with the date, time, and cause of the event. By pressing the View Data button, the user can access another window where all the information involving the electrical magnitudes appears, along with the option to print or save this information by pressing the corresponding buttons. Select which events to save or print by ticking the boxes in the Select column. Selecting the New Snapshot Events option allows the user to visualize all the snapshot events since this window was open for the last time. Oscillography. In Actual Records Waveform Capture is the window which displays a list of oscillography records available in the relay, up to 999 entries. This screen allows the user to select the records to be saved among all the records available. The download of the oscillography from the relay to the PC is accomplished through the Download button that appears in the Waveform Capture window. The screen will show all the available records in the relay, and by clicking on each of them, the system will display the heading information for that record. Once the file is downloaded, you shall be able to open it with a ComTrade file reader such as the EnerVista GE-UR setup program. This software can be freely downloaded from the GE Digital Energy website. In this advanced section of the records, we shall take a look at the control events, fault recorder, and data logger features. Control events. The Control Events table is found under Actual, Records, Event Recorder, Control Events. This table is equal to the Snapshot Events tables, except it only displays control events. These are the events configured in Setpoint, Relay Configuration, Events. There are 128 configurable events and 64 non-configurable switchgear events. Events displayed in red are activated, whereas the events displayed in black are in standby. Fault Recorder. The Fault Recorder is a tool located at Actual, Records, Fault Report. It displays a screen similar to the oscillography downloading tool. It shows the number of reports stored in the relay. Selecting one of these reports by pressing the View Header button displays the date, time, line setting, breaker and recloser, pre-fault, fault, and the fault distance information. This file can be downloaded to the computer in a CSV format file. Fault report file retrieval can be performed via serial or Ethernet communications. However, please note that any settings change in the fault report will produce the removal of all the information stored up to that moment. Data Logger. The data logger is a tool that monitors analog values. Before use, It is necessary to configure this tool by navigating to Set Point, Product Setup, Data Logger. Select which analog value to monitor in each channel and the sampling rate. To view the recorded information, go to Actual, Records, Data Logger. In this screen, the user will see when the first and last samples were taken and graphical representations of the analog signals. For further analysis, this data can be downloaded in a ComTrade format via Ethernet communications. Note again that changing any setting in the data logger will erase all of the logged information in the relay. There are two key measures applied to the F650 setup designed to enhance its security. First, users can be created with limited access to only certain elements in the program, and second, each user can be assigned a unique access password to the program. We shall look at both of these possibilities. There is no security enabled by default. New users can only be added by users who have administrator rights. To add a new user, go to Security, User Management, and name a new user in the Username column. By ticking the checkboxes to the right, this new user will be given the power to view and manipulate different elements in the relay. To erase a user, tick the Delete entry in the User Management window and press the OK button. For detailed information on each of the powers users can be given, refer to the manual. Ticking the Enable Security checkbox will enable the EnerVista 650 setup to prompt for a username and password each time the program is started. The default password for every new user will be password. The program will ask the user to change it the first time he or she logs in. The password can also be changed in Security, Change Password, or change the user in Security, Login User. The application also requires the user to enter a personal question in case the password is forgotten, which is accessed by pressing the Forgot Your Password button.